Hi guys, welcome back. I want to spend a little bit of time with you guys today talking about pH curves, um, which I'm going to demo for you in the classroom so that you get a chance to see this pH curve. Now, for our intents and purposes in this level, the only types of curves that you need to be able to analyze and understand are the strong acid, strong base pH curves. And for all of these pH curves, they're always going to have a shape much like this particular graph that I've given you guys in the notes. Now, a pH curve is generated when we take either a strong acid or a strong base, and that we place in our Erlenmeyer flask. So this is what we call our sample. We place either the strong acid or the strong base in our Erlenmeyer flask. Now in this case, what I've done is I've taken a strong base, and I have placed a certain amount, and we place an amount with a very precise volume. So we actually pipette this amount of strong acid into the Erlenmeyer flask, and this is the sample. You may also see this called the analyte. That's another name for this. Generally, we refer to it as the sample, but do realize that if you hear analyte, they're referring to the solution that's in the Erlenmeyer flask. Now, what we do, and we'll talk more about glassware and all of that kind of stuff when we talk about titration analysis specifically. But what we do in a pH curve is we add, if we've got a strong base as our sample or our analyte, we add a strong acid to it in this case. And what we're looking for is, generally, if we're doing a titration analysis, we're looking for that point where all of the hydroxide ions in the sample have been neutralized by all of the hydronium ions that are being added to the sample. So if you can imagine us, measuring the pH of this sample, we're dealing with a strong base, which means that our pH is going to be relatively high to start, right? When our volume of titrant added, let's add a little label here. When our volume of titrant added is 0. Okay, so when it's just strong base in the Erlenmeyer flask and we've added 0 milliliters of titrant or 0 milliliters of strong acid, our pH of that sample is going to be roughly about 13 in this case. So because this first starting point is very, very high, this starting point tells me that our sample is a strong base. So this particular starting point, when I read this graph, tells me that whatever was in that Erlenmeyer flask had to be a strong base. Now, initially, when we start adding titrant to that sample, the titrant is going to have very, very little effect on the pH because there's going to be such a high concentration of hydroxide in that sample that little bit of hydronium that we're adding to the sample is going to do very little to change the pH. So at this point that I've labeled point B, we still have excess hydroxide. So even though, here I've got over here for you, even though the hydronium is being added, and yes, we've got hydronium in the flask, it's pretty much being neutralized, or it's turning into water right away because there's plenty of hydroxide in the Erlenmeyer flask, and after it neutralizes that hydronium that was just added, there's still excess hydroxide. So that means that the pH is going to be very, very high still. There's not going to be a very big change in pH at this point. But the more volume of titrant or the more volume of strong acid we add to that strong base sample, there's going to come a point where we're going to start observing that the pH actually does start to change because now the amount of hydronium that's in there is starting to become equivalent to the amount of hydroxide. So if you can kind of imagine it like a teeter-totter, right? We're adding more and more hydronium, so that teeter-totter is leveling out. And as that teeter-totter levels out, remember, we start moving toward a pH of 7. And what you're going to observe here is you're going to observe, this is that rounding point here on the curve, where you're going to start to see your pH starts to decrease because that hydronium is having a larger effect on the sample. Typically, when we do this, we'll measure, we'll add a little bit of titrant, we'll measure the pH, and we'll continue. The other thing we can do as well, so that we know qualitatively when we're approximating that point where we're going to reach a pH of 7, we can have a indicator in our sample as well. And so at this point here, where this line starts to curve down on us, where we start to see a change in our pH, that's the point where you're going to start to see the color change in your sample. So you're going to start to see, a burst of color change, but pretty much as soon as that burst of color changes, it reverts back to its original color. Now, there's going to come a point where 1 drop of titrant is going to send us from a relatively high pH down to a pH of 7 and all the way down to a pH of acid. Because at this point, that 1 drop of strong acid will neutralize whatever excess hydroxide was in it. So that's point C. It'll neutralize whatever excess acid was in it. And there's probably going to be some hydronium left over, now excess hydronium, that didn't get neutralized with the base. And so that's what's going to drive your pH down to this very, very low pH. So this point C is an important point for us when we talk about titrations. This point C is what we call the equivalence point. And the equivalence point in a strong acid, strong base titration is the point at which every hydroxide ion, or every, all the concentration of hydroxide ion in your sample is neutralized by all of the hydroxide ions in the titrant in this particular example. So the stoichiometric ratio between hydroxide to hydronium has been achieved at this point. We have a neutralization reaction. And basically at that point, you have salt water, right? You've completely neutralized the sample, and all you have left is your salt and your H2O, right? Now, because we end up with excess hydronium, right, since that OH was neutralized, but there's probably going to be some excess hydronium that doesn't get neutralized, that's going to dip our pH down much lower than a pH of 7. And at this point, we have excess hydroxide. And if we continue to add titrant, if we continue to add strong acid, you're going to see that there's going to come a point where that pH is going to level off again, because now you've just got excess hydroxide, and there comes a point where your pH doesn't change anymore, since the concentration of hydroxide is equivalent with every drop of titrant that you're adding into the sample flask. Okay, so that's essentially what takes place when we do a pH curve. For us, when we get into stoichiometry, because we are going to get into stoichiometry, when we get into stoichiometry, for us, what we're interested in is what is the volume at which this equivalence point takes place. So on our graph, what we would be interested in here is reading what volume this equivalence point, which is the midway point of this steep line, at what volume does that happen? Okay, and that's how we're going to collect our data. When we were talking in previous units about stoichiometry, the data was always given to you, right? So they said, 10 milliliters of sodium hydroxide with a concentration of 0.15 moles per liter is mixed or reacted with 12.5 milliliters of hydrochloric acid. What is the concentration, right? We always had a word problem. Now what we're going to do is we're going to pick the information off the graph. And specifically, we would be looking for what is the volume of hydrochloric acid, if this is our strong acid titrant, that was added to our 10 milliliters of sodium hydroxide, if that's what was in the sample. Okay. So we're going to do this in the lab. Actually, we're going to generate a curve like this. I'm going to demo this for you guys so that you get a chance to see in real time what's happening here. And I'll go over this later again with you guys, but this is essentially what the setup is. You've got your Erlenmeyer flask here with your strong base sample. We'll have a pH probe that'll measure the pH for us. This piece of glassware is called a burette, and inside the burette is our titrant, or our strong acid in this case. If strong acid is in the titrant, strong base has to be in the sample. And if strong base is your sample, if strong acid is your sample, strong base has to be your titrant. So it's always, if base is in the one, acid has to be in the other, right? Now, a couple of other important pieces of vocabulary for you for right now, and we will come back to this setup when we talk titration analysis. The equivalence point. The equivalence point I showed you on the graph is here. It's the midway point. For a strong acid, strong base titration, this equivalence point always, always, always happens at a pH of 7. Okay. Next course, you guys will look at what happens when you react a strong acid with a weak base, or a weak acid with a strong base, right? And then you'll get into that. But for a strong acid, strong base, which is what you guys are responsible for, that'll always happen at a pH of 7. So do remember that pH of 7 because it is important for you guys. Okay. And the equivalence point, definition-wise, the equivalence point is a quantitative observation. Right, so what we're looking for is that volume of titrant that is added, the exact volume, of titrant required to neutralize the sample, right? So it's a quantitative observation. In this case, we can see that because we've got our pH probe measuring for us. If we were doing a titration analysis, which we'll talk about more later, if we were doing a titration analysis, remember I talked about having our indicator here and how we would start seeing the change in color when we start rounding the pH here, when we start dropping in pH. The equivalence point will happen when that color change is permanent, right? So now we've dropped to this very low pH, we will see a permanent color change. And when we talk permanent color change, we're talking about a change of 30 seconds or more. Okay, so it's a quantitative observation. We're looking for that exact volume. The endpoint I have here as well, the endpoint is a qualitative observation. So when we see that permanent color change, we'll know that our titration analysis is finished. Because in a titration analysis, really, we don't care about this excess H30 plus portion. In a titration analysis, as soon as we reach this low pH and that color change is permanent, we're done. Because we're only interested in getting this volume. In a pH curve, generally if our goal is to generate a full, complete pH curve, then yeah, at that point, I'll keep going past the equivalence point and I'll keep going until I don't see a change in pH anymore. And for me here, this is my end point right here, because that's where I'm stopping my titration. So the endpoint is a qualitative observation when we talk titration analysis, and that qualitative observation is when we see a permanent color change of 10 seconds or longer. 10 seconds or longer, I said 30 seconds before. 10 seconds seems a little bit slow on the time side for me. But, somewhere between 10 and 30 seconds, let's say. Okay. And then that point D, like I said, is the point where there's no more hydroxide and there's excess hydronium. Okay. This is really important for you guys to remember, these definitions. So your equivalence point is that quantitative observation when all of the hydroxide ions have been neutralized by all of the hydronium ions, right? And at that point, we have a pH of 7, exactly. The endpoint for our purposes right now, talking pH curve, the endpoint is whenever we stop the titration or for this pH curve. In a titration analysis, the equivalence point will happen when we see that permanent color change, that qualitative observation. And we'll do a titration analysis afterwards, but for right now, let's just focus on the pH curve. Now, I want to show you the flip side. So let's do an example here where instead of having the strong base as our sample or our analyte, now we put our strong acid here. And in our burette, we put our strong base titrant. Okay, so in this case, when we start at a volume of 0, we're going to have a high concentration of hydronium ions. And because this is a strong acid, that means our pH is going to be very, very low. So that's our starting point right there when we've had 0 milliliters of volume titrated. Okay. Now, as soon as we start adding little bits of strong base to the sample, again, same idea. We're going to see very little change in our pH because as soon as those drops of hydroxide enter the sample, they're going to neutralize with the hydronium that's in there, but there's going to be plenty of excess hydronium still left in the sample, and so your pH isn't going to change very much. But there's going to come a point as we add more and more hydroxide ions to the sample, there's going to come a point where the hydroxide ions are going to they're going to start forcing a pH change because now they're starting to overwhelm the hydronium ions in solution, right? And so we're going to start seeing that as those hydroxide ion as the hydroxide ion concentration increases, you're going to start seeing that there's a curve in this pH, right? In this pH data. And if we've got indicator here, that's where that color change is going to start taking place. But as soon as we see the color change, it pretty much disappears. There's going to come a point where one drop is going to change that pH. It's going to neutralize. So all of the hydroxide ions that go in with that one drop will neutralize whatever hydronium ions were remaining. And more than likely, because it is a strong base, there's going to be excess hydroxide in that drop that doesn't get neutralized. And so that's going to send your pH shooting up past your pH of 7, up past your equivalence point. And this is the point where we're going to see that permanent color change of, 10 to 30 seconds. And again, that pH of 7, that's your equivalence point. In our titration analysis, this is where our end point would be. Because I'm wanting to generate a pH curve here, I continue adding hydroxide, and then there's going to come a point where my pH is going to level off because the concentration of hydroxide ions won't change. Okay. So this is when we're adding strong base to our strong acid. Now I'm going to skip over the next section of notes because I don't want to get into the stoichiometry just yet. We're going to come back to it later. Okay. Now, again, our equivalence point happens at this pH of 7, and quantitatively, what I'm interested in is what is that volume of titrant? What is that volume of strong base that we had to add in order for all of our hydronium ions to be completely neutralized? So at this point right here, all we would have is water and salt, some ionic salt. Okay, now I want to show you what's happening in this case. So we're just going to jump down. I'm going to skip the stoichiometry. I want to jump down here to our net ionic equations because I want to show you what's taking place here. So in that previous graph, we had a strong acid as our sample. And I'm just going to put here for you guys so you can see. This is our sample. And we had a strong base as our titrant. And so you guys saw that the first data point had a very, very low pH, and we were adding strong base to it. At equivalence, at the point at which the pH is 7, all we will have in solution are is water, and sodium ions and chloride ions will be in there. They're spectator ions, but all we'll have in there is basically water. That's it. Okay, so if we were to do our total ionic equation here, this will ionize, right? This ionizes into hydrogen ion and chloride ion. This dissociates into sodium ion and hydroxide ion. This dissociates into sodium ion and chloride ion. And the water is low solubility, so it doesn't separate. Our sodium and our chloride ions, they cancel out because they're spectators. And so this was, when we did net ionic equations last unit, this was our net ionic equation for a neutralization reaction. The reason that we have water being produced, or that pH of 7 being produced, is because all of the hydroxide ions are pairing up with all of the hydrogen ions to produce water. So this here is what's happening at equivalence. This is what's happening at the equivalence point. All of these hydrogen ions are pairing up with these hydroxide ions to produce water liquid. Before that, we weren't producing, well, we were producing some water liquid, but the thing was that we had too many hydrogen ions and not enough hydroxide. So at that point, yes, all the hydroxide was getting paired up with hydrogen, but there was excess hydrogen. So our pH was still really low. At equivalence, we had an equal concentration of hydrogen ion and an equal concentration of hydroxide. And so all we've got in there now is your water. And that's why the equivalence point for your pH curve is at 7, right? And then if we added excess hydroxide to that, then we ended up on the flip side. We added excess hydroxide. We added excess hydronium ion, and there wasn't enough at that point because there's no hydroxide left because we've just neutralized it all, and we've got excess hydronium, now our pH spikes in the opposite direction. So hang on, I think I messed that up for you guys. So I just want to repeat that one more time. When we start, we have our sample. Our sample has excess hydrogen ions, and we're adding hydroxide to it. So these hydroxide ions are being paired up with a hydrogen to produce water, but there's not enough of these ions to completely pair up. So there's excess of this hydrogen, which means that your pH stays low. At equivalence, we've added enough of these hydroxide ions to pair up with the hydrogen ions, which means that we've used all of the hydrogen ions that were in the sample, in the Erlenmeyer flask, and we've used up all of the hydroxide ions. And so now in that sample, all we have is water. If we add more titrant to the sample, well, at that point, there's no more hydrogen ions left up because they were all paired up to produce water. There's no more of these guys. So if we continue adding titrant, all we have is hydroxide at that point. And so that's why eventually your pH levels off, because at that point, once you've, balanced out the amount of base with the amount of water that you produced, you're going to end up producing a level pH at that point, because the concentration of the base is going to balance out. Now, the thing that I want to show you guys, though, is this was what our net ionic equation was in the previous unit when we were still talking about Arrhenius referring to hydrogen ion as your primary acidic substance, right? In this unit, we've revised that definition so that now, instead of it being hydrogen ion, now we talk hydronium ions in solution. And so instead of it being hydrogen ions, what's important for you guys is that it becomes hydronium ions pairing up with hydroxide. The hydronium gives a hydrogen to the hydroxide, and we end up producing 2 waters as a result. So this is our revised, modified Arrhenius net ionic equation that you need to remember. Make sure you remember this one. So At equivalence, if it's a strong acid, strong base scenario, that's the point at which all of these hydronium ions have paired up with all of these hydroxide ions, and we've produced just the water. This net ionic equation is what we're observing when we reach that equivalence point, right? And then on either end of the equivalence point, we either have excess hydronium or we have excess hydroxide, right? So that's what I want to talk about with pH curves. That's where I want to leave it. I'm going to talk, we'll do another lesson talking about titration analysis specifically, and then we'll talk about the stoichiometry. So bring your questions to class. We will demo this in class so that you can see that pH curve being generated. You guys will be doing that in real time with me when we get into class. And as always, guys, I hope you guys are doing well. Stay safe, and we will chat soon. Take care.